I want you to just imagine a stretch of the ocean where the fundamental physics of water just seem to completely break down.
Right, like an area that operates less like a normal body of water and more like, I don't know, a planetary scale wood chipper.
Yeah, exactly. Picture a 600-mile expanse of open sea that has, over the centuries, swallowed thousands of ships.
Thousands. And claimed the lives of roughly 20,000 sailors.
It's terrifying. I mean, this is a place that routinely generates waves the size of an 8-story office building, and the wind sweeping across this water literally never stops.
Never. Because if you look at that latitude on a globe, there is not a single square inch of landmass anywhere to create friction and slow that wind down.
Which is just wild to think about. Welcome to our deep dive into the Drake Passage. We have an incredibly dense stack of sources in front of us today, pulling from, contemporary oceanographic research, marine biology logs.
Some deeply unsettling marine biology logs, I should add.
Oh, definitely. Plus centuries of maritime history and structural geological data, including telemetry from some recent deep sea explorations.
And our mission for this deep dive is to look well past the sheer terror of navigating this crossing. I mean, hidden within that extreme hostility is this profound paradox.
Right, because this isn't just about a scary ocean. We are going to unpack how the most violently destructive environment on Earth is secretly the planet's most vital engine.
Yeah, a mechanism responsible for global climate stability, unimaginable biological abundance, and some of the most radical evolutionary problem solving we've ever actually observed.
The sheer scale of the mechanics at play here is staggering, and I want to start with the actual geography because, well, the architecture of this space really dictates everything else.
It does. It's the foundational blueprint.
If you look at a globe, the Drake Passage looks almost like a geographic error. It's this relatively narrow, 600-mile wide gap situated perfectly between the very tip of South America down by Tierra del Fuego and Cape Horn and the Antarctic Peninsula.
And the key to understanding the hostility of that specific gap is looking at the latitudes that contain it. It is literally the only place on our planet where the ocean can completely circle the globe without ever intersecting a continent.
Which is so unique.
Right, because if you look at, say, the Pacific or the Atlantic or the Indian Oceans, their currents are eventually forced to interact with land masses.
They hit a coast or something.
Exactly. They hit a continental shelf, they deflect, they fracture, and their kinetic energy dissipates. But that terrestrial friction is entirely absent down here.
So all that energy just compounds. You have the Antarctic Circumpolar Current, which is squeezing roughly 15 million cubic meters of water per second through this specific gap.
15 million. It's a number that's almost hard to conceptualize.
It really is.
Yeah.
So let's unpack this and give you some perspective. If you took the combined flow of every single river on planet Earth,
The Amazon, the Nile, the Mississippi.
all of them, every river, and you multiplied that volume by 100, you would just be approaching the volume of water moving through the Drake Passage. It's just massive.
So imagine taking a fire hose containing all the world's rivers, blasting it through a slightly open door, and simultaneously firing hurricane-force winds in the exact opposite direction. That is the Drake Passage.
That's a perfect analogy because the fluid dynamics of that pinch point create a scenario where extreme hydraulic force meets extreme atmospheric force.
It's a collision.
Exactly. That 15 million cubic meters of water is merely the hydraulic bottom half of this engine. Above the water, you have this permanent atmospheric collision.
Right, because there's no land to block the wind.
No landmass to interrupt the fetch being the distance over which wind blows. So the air in the Southern Ocean accelerates continuously over thousands and thousands of miles.
Wow.
And the incredibly dense, freezing polar air pouring off the Antarctic ice sheet acts almost like a physical wall moving northward, and it just slams directly into the warmer, moisture-heavy air drifting south from the subtropics, which creates this relentless atmospheric pressure gradient. I mean, the sailors who historically tried to map this area gave these latitudes monikers that sound like they belong in some gothic horror novel.
Oh, yeah. The Roaring 40s.
The Furious 50s and the Screaming 60s. But the crazy thing is, those aren't just colorful sailing idioms. Meteorologists actually use those terms to classify the permanent wind shears at these specific degrees of latitude.
The operative word there being permanent? I mean, the Drake Passage is not a region that experiences frequent storms. It is a permanent condition.
It's just always like that.
Right. A storm implies a localized, temporary anomaly that will eventually pass,
Yeah.
allowing the sea state to return to a baseline of calm.
But in the Drake Passage, calm is the anomaly.
Precisely. The engine is running on a perpetual closed loop. Atmospheric winds maintaining force 8 on the Beaufort scale, which is gale force, blowing consistently between 40 and 50 miles per hour. That's just the baseline state of affairs.
And all of that invisible kinetic energy, all of that planetary pressure eventually has to manifest physically. It transfers directly into the surface water, which brings us to, well, the reality of the humans who have to operate vessels in this environment.
And it is not a forgiving environment.
Not at all. The normal everyday sea state here produces waves sitting between 10 and 20 meters. That is 30 to 60 feet on a standard Tuesday afternoon.
Just a typical day.
Right. But during heightened storm activity, which again is near constant, these waves easily exceed 25 meters. We're talking about an 80-foot vertical wall of freezing opaque water traveling across the ocean at highway speeds.
And the danger isn't solely a function of the wave's vertical height. It's heavily dependent on the frequency, the period between the waves.
Which is where that pinch point comes in again, right?
Yes. The wide expanse of the Southern Ocean acts as this massive funnel. So as that oceanic energy is forced down into this narrow 600-mile corridor, the wave energy is physically compressed.
So the waves literally have nowhere to go but up.
Exactly. They can't spread out horizontally, so the energy translates vertically. The waves grow significantly taller, the faces become dramatically steeper, and the distance between the crests violently shortens.
It completely changes the rhythm of the ocean. Instead of long, rolling swells that a ship can just sort of ride up and down, it's like a crowd of people suddenly forced through a narrow turnstile.
The hydrodynamic impact on a vessel is punishing. A ship just doesn't have time to recover its pitch or roll before the next wave impacts the hull. It's a relentless, staggering sequence of kinetic strikes.
People taking modern research vessels or luxury expedition ships to Antarctica actually call this the Drake Shake.
It's a highly accurate term.
It sounds like it. It's this grueling 2-day endurance test where just basic human functioning becomes nearly impossible. Some of the maritime logs in our sources noted that in the galleys of these billion-dollar vessels, they have to deploy industrial sticky mats on the dining tables.
Just to keep the plates from flying around.
Exactly, just to prevent plates and heavy glassware from turning into projectiles. And this is occurring on ships equipped with state-of-the-art inverted bows and advanced gyroscopic stabilizers.
Which really makes you think about the historical context. If active computational stabilizers are struggling today, imagine doing this 100 years ago.
I can't even fathom it.
Prior to the Panama Canal opening in 1914, this route and the adjacent Magellanic channels was the primary maritime artery connecting the Atlantic and Pacific Oceans.
So merchant fleets, whaling vessels, military armadas, they all had to transit this space.
They had no choice. And hundreds of heavily laden ships and thousands of highly experienced sailors were simply erased by this ocean.
Erased. That's a chilling way to put it.
But it's true. In an era before satellite telemetry and long-wave radio, a ship didn't send a distress signal. It just never arrived at its destination.
The margin for error is basically non-existent. I mean, in 2019, a highly advanced subsea research vessel packed with modern sensors took a roll that nearly resulted in a catastrophic capsize.
That's with modern tech.
Right. And this constant baseline violence sets the stage for the absolute apex of nautical terror, which is rogue waves.
Oh, rogue waves. Yes.
These are asymmetrical, structurally unstable walls of water capable of applying enough focused metric tonnage to shear a steel hull completely in half. But for decades, didn't the scientific community treat rogue waves as maritime mythology?
They did. They threw it right up there with sea monsters and krakens. The prevailing fluid dynamics models of the 20th century utilized these linear mathematical formulas to predict wave behavior.
It's in Gaussian distributions.
Exactly. And according to those Gaussian distributions, a wave cresting over a certain magnitude rising vertically and breaking the standard distribution of a sea state was statistically improbable to the point of impossibility.
Like, the math stated they could only occur once every 10,000 years.
Right. But then in 1995, empirical data forced the scientific community to totally rewrite the models.
This is the Dropner oil platform incident. Yeah.
Yes. In the North Sea, the platform was equipped with downward-facing laser sensors to continuously measure the sea state. And on New Year's Day, that laser recorded a direct hit from a wave that reached nearly 26 meters in height.
Wow.
Rising out of a surrounding sea state that theoretically should not have possessed the requisite energy to produce it. The laser telemetry essentially proved that the folklore was a physical, measurable reality.
It's kind of a humbling moment, isn't it, when the ocean forces you to realize your fundamental math was just entirely wrong.
Very humbling. And the mechanisms driving the formation of these rogue waves, particularly in the Drake Passage, they rely on nonlinear wave dynamics.
What does that mean, practically speaking?
The primary theory is constructive interference. Because the Drake is subjected to storms from multiple cardinal directions, you have distinct wave trains, sets of swells generated thousands of miles apart, moving at different frequencies.
Okay, so they're crisscrossing.
Normally, these wave trains just pass through one another, temporarily altering the surface before continuing. But under specific chaotic conditions, the crests of these distinct wave trains fall perfectly into phase.
Meaning they line up exactly.
Exactly. They align and stack on top of one another, instantaneously multiplying their kinetic energy and vertical height into a single massive peak that only exists for a few agonizing minutes before collapsing.
And there's an entirely separate mechanism, too, involving the deep currents themselves acting as a magnifier, isn't there?
Yes, there is. When a highly energized surface swell runs in direct opposition to a massive, fast-moving underlying current, which happens continuously in the Drake, the current acts upon the wave energy almost like an optical lens, focusing diffuse light into a concentrated point.
Oh, wow.
The opposing current forces the wavelengths to compress. The kinetic energy have absolutely nowhere to travel but straight up, building a vertical wall of water that eventually becomes too steep to support its own mass.
Okay, I have to challenge this a bit, though. Because we operate in an era of unprecedented technological observation.
We do.
We have constellations of oceanographic satellites. We drop autonomous buoys across the globe. We run predictive AI models that can accurately forecast a rainstorm over my specific neighborhood down to a 10-minute window. Are you saying we possess zero capability to predict when one of these steel-shattering waves is going to manifest?
I am. The forecasting models simply cannot compute the variables fast enough. The fluid dynamics at play are fundamentally chaotic.
So we're just flying blind.
We can predict that a specific sea state is highly conducive to rogue wave formation, sure, but no current technology can pinpoint the exact coordinate and exact second one will rise.
That is terrifying.
Somewhere in the Drake Passage, right at this very moment, multiple wave trains are sinking in phase, quietly building a 60-foot vertical wall of water in the dark, and no one will see it until the moment of impact.
That concept alone is enough to keep anyone on dry land forever. But the surface violence, as terrifying as it is, acts essentially as a chaotic lid. Because when you penetrate just a few meters below that churning water, you cross an invisible threshold that fundamentally rewrites the biological rules of our planet.
It really does. To understand the biology down there, we have to examine the hydrographic boundary, known as the Antarctic convergence, or the polar front.
This invisible underwater cliff.
Exactly. As you travel south through the Drake Passage, you eventually hit it. But it isn't a geological feature made of rock. It is constructed entirely out of dramatic shifts in temperature and water density.
The sources describe it almost like a thermal shock wall. I think we naturally view the ocean as this continuous, borderless medium where marine life can just freely migrate wherever. But this convergence is a hard physical border.
A very hard border. Species that evolve to thrive in the slightly warmer, less dense waters north of this invisible cliff simply cannot endure the physiological shock of crossing it.
Because it's so abrupt, right?
Incredibly abrupt. The line demarks the exact zone where the incredibly cold, highly dense, nutrient-heavy water flowing north from the Antarctic continent directly impacts the relatively warmer, lighter water drifting south from the subantarctic regions.
And since cold water is denser,
it sinks rapidly. Because of the density differential, the frigid Antarctic water rapidly subducts. It dies deeply beneath the warmer water. The surface temperature of the ocean can plummet by several degrees across a distance of just a few kilometers. It functions as a hermetic biological moat.
A biological moat, which leads us right into the core paradox of the Drake Passage that we mentioned earlier. The unrelenting violence we just explored, the crushing pressure gradients, the massive currents, the rogue waves. That specific violence is the mechanical engine responsible for one of the most astonishingly productive biological zones on Earth.
It really forces us to reframe how we view extreme environments entirely. Often when we observe extreme habitats like arid deserts, deep subterranean caves, or the death zone on Everest, we categorize them as places where biology merely endures.
Right, like life is just stubbornly holding on.
Grudgingly holding on, colonizing a space despite the hostile parameters. But in the Drake Passage, the biomass does not exist in spite of the violence. It exists entirely because of it.
The mechanism driving this is upwelling, but it's operating on a scale that is almost difficult to process. You have the violent atmospheric stirring at the surface, interacting with the deep underwater topography.
Because there are massive submerged ridges and mountain ranges in the passage, like the Shackleton Fracture Zone.
Right, and those geological features act as bathymetric ramps. The incredibly powerful deep water currents, which are carrying centuries-old water loaded with heavy concentrations of silica, nitrates, and iron from the ocean floor, they slam into these submerged mountains.
And that kinetic energy has to go somewhere.
Exactly. It forces that deep, freezing, nutrient-dense water to surge upward along the rock face until it violently erupts into the photic zone, the sunlit layer of the surface ocean.
It is essentially a planetary-scale nutrient delivery system. And the moment that deep-sea fertilizer hits the sunlight, it triggers a massive biological chain reaction.
Phytoplankton blooms.
Massive ones. Microscopic phytoplankton bloom in quantities so vast, they literally change the color of the water. And those blooms provide the grazing ground for billions of tons of Antarctic krill.
Which in turn feeds everything else.
Everything. That swarm of krill supports an entire ecosystem of apex predators, the penguins, the leopard seals, and most notably, the whales.
Like the blue whale.
Yes, the blue whale, which is the largest single organism to ever exist in the history of the planet. I mean, significantly larger than any terrestrial dinosaur. It migrates thousands of miles specifically to feed in this violently churned corridor.
It's incredible. The storm systems possessing the kinetic force to snap modern ships in half are the exact same mechanisms fueling the metabolic requirements of the largest animal on Earth. The destruction and the creation are inextricably linked.
They are two sides of the exact same coin.
But, visiting this corridor for a seasonal buffet is very different from evolving within it. If an organism lives permanently in the Drake Passage, standard evolutionary pathways are completely insufficient. The environmental pressures are so extreme that biology is forced into profound, hyper-specific problem solving.
Right. The adaptations required to survive here represent biology operating at its absolute mechanical limits.
Take the sky above the passage. The wandering albatross is an avian marvel. It has an 11-foot wingspan, the longest of any living bird.
11 feet is massive.
Now, intuitively, if you were tasked with engineering a bird to survive the most violent, relentless winds on the planet, you might design something compact, heavily muscled, shaped like a bullet to piece the gales. But the albatross is the exact opposite.
It looks fragile almost.
Right. It's a massive, fragile-looking glider.
Well, the albatross survives by completely refusing to fight the wind. Instead, it extracts kinetic energy from the storm itself through a highly complex flight mechanic known as dynamic soaring.
Dynamic soaring, how does that work?
The bird constantly navigates the boundary layer of the wind. There is a sheer differential between the rapidly moving air, high above the wave crests, and the slower moving air that is being dragged by friction directly across the water's surface.
Well, it's weaving between those layers.
Continuously. The albatross continuously loops through this sheer gradient, climbing into the fast wind to gain velocity, then swooping down into the slow wind to gain distance, over and over again.
It is effectively turning the ship-breaking gales into a free, infinite fuel source.
And its internal anatomy is heavily modified to support this. They possess a specialized tendon-locking mechanism located in the shoulder joint. Once they extend those 11-foot wings, the joint mechanically locks into place.
So they don't even have to use muscle power to keep their wings out.
Practically zero muscular energy. Telemetry data has actually tracked these birds traversing over 1,000 kilometers in a single day across the Drake Passage without flapping their wings more than a handful of times.
1,000 kilometers without flapping. That is insane.
The biomechanics are fascinating. But the neurological requirements of dynamic soaring pose a significant question in behavioral biology too.
Because it requires so much brain power to calculate.
Exactly. The albatross is making constant split-second micro-adjustments to its pitch and yaw in order to perfectly ride an invisible, chaotic gradient of wind shear. The cognitive processing speed required to literally read the topography of the wind is immense.
And they just know how to do it.
Well, biologists have long debated whether this highly complex maneuvering is a learned behavior honed through trial and error, or if the algorithm is entirely instinctual. Because when juvenile albatrosses launch into their first solitary flight over the open ocean, there are no adults flying in formation to teach them the precise mechanics of dynamic soaring.
So the survival software is fully compiled and active before they even crack their shells.
It seems that way, yes.
But as elegant as the adaptations in the sky are, the biology operating down in the freezing depths of the passage forces us to rethink what constitutes a vertebrate entirely. Let's look at the Antarctic icefish.
Oh, the icefish. It represents an evolutionary leap that just defies standard physiological logic.
If you were to bring an icefish to the surface and extract a blood sample, the fluid in the syringe would not be red. It wouldn't even have a pink hue.
Not at all.
The blood is entirely translucent. It looks like dirty water.
Because they are the only known lineage of vertebrates on the entire planet that completely lack hemoglobin.
Which is the protein that carries oxygen.
Right. Hemoglobin is the iron-rich metalloprotein found in red blood cells that binds to oxygen in the respiratory organs and transports it to the tissues. For every other vertebrate in existence, the sudden absence of hemoglobin is synonymous with immediate cellular asphyxiation.
So wait, let me get this straight. If they don't have the biological delivery truck to move oxygen from their gills to their organs, how are their tissues not undergoing immediate necrosis? I mean, how does an animal breathe without hemoglobin?
The survival of the icefish relies entirely on the unique thermodynamic properties of the Drake Passage. The temperature of the water here hovers constantly near the freezing point of seawater.
Which is colder than regular freezing, right?
Because of the salinity, yes.
Yeah.
It's roughly negative 1.9 degrees Celsius, slightly colder than the freezing point of fresh water. And the physics of gas solubility dictate that cold liquids can hold significantly higher concentrations of dissolved gases than warm liquids.
So the freezing water itself is just hypersaturated with dissolved oxygen.
Exactly. The environment is so oxygen-rich that the icefish evolved away from needing a specialized carrier molecule entirely.
They just ditched it.
They ditched it. Instead, they adapted an incredibly high total blood volume and a massively hypertrophied heart to constantly pump that clear, watery plasma throughout their system.
Wow.
Furthermore, they entirely shed their scales. Their bare, heavily vascularized skin functions as a massive supplementary respiratory organ, allowing oxygen to diffuse directly from the highly saturated water straight into their bloodstream.
Here's where it gets really interesting, though. Because there is a profound, almost tragic irony in this level of adaptation. The icefish is so flawlessly engineered to exploit this very specific thermodynamic extreme that it is now essentially trapped in an evolutionary dead end.
Trapped by its own success.
Exactly. The absolute cold that enables its survival is its single greatest vulnerability.
You're highlighting the inherent danger of hyperspecialization here. The icefish evolved over millions of years under the assumption of a static, permanently freezing ocean. Its entire cardiovascular architecture relies on the high oxygen solubility dictated by that specific temperature.
And we know the ocean is no longer static, the thermal baseline is shifting.
Climate change is actively warming specific regions of the Southern Ocean by mere fractions of a degree. But in this ecosystem, a fraction of a degree is a seismic event.
Because the physics change.
Right. If the water temperature rises even slightly, the liquid's capacity to hold dissolved oxygen precipitously drops. For a creature lacking hemoglobin, a slight warming trend triggers systemic hypoxia.
They literally suffocate in the water.
Millions of years of brilliant, radical adaptation could be completely unraveled by a 2-degree thermal shift. It's a pace of change that completely outstrips the species' capacity to evolve a new respiratory solution.
It perfectly illustrates that evolution isn't striving for an ultimate, indestructible form. It is a blind mechanic, just solving the immediate problem of the environment directly in front of it. And while the icefish solved the cold by altering its biochemistry, other creatures adapted to the freezing dark by breaking the rules of size altogether.
Polar gigantism. It is one of the most jarring visual phenomena encountered in deep-sea marine biology.
The scale of the invertebrates down there defies terrestrial logic. We are talking about pycnogonids, sea spiders. Now, in warm, shallow coastal waters, sea spiders are minuscule, often requiring magnification to study.
Barely visible.
But in the deep waters of the Drake Passage, they possess leg spans reaching 20 inches across. They're the size of a large dinner plate.
A spider the size of a dinner plate.
Yep. You have giant isopods crawling along the abyssal plain that look identical to the little pill bugs you find under a damp log, but they are the size of a football. You have scyphozoans, jellyfish, possessing bells that dwarf their temperate counterparts. Why does an environment of crushing pressure and freezing temperatures induce gigantism?
Well, the scientific community is currently divided between two primary hypotheses, though honestly, neither offers a universally clean explanation.
Let's hear them.
The first model builds directly on the thermodynamic principles we just discussed with the icefish, the oxygen temperature hypothesis. Many of these invertebrates, like the sea spiders, do not possess lungs or gills. They rely on passive diffusion, absorbing oxygen directly across their cuticle.
Like the icefish absorbing it through their skin.
Similar, yes. In warmer waters, the low concentration of dissolved oxygen acts as a strict biological governor on body size. If an organism grows too large, its surface area to volume ratio drops, and it can no longer passively absorb enough oxygen to supply its internal tissues.
But in the deep drake, that biological governor is removed by the sheer density of dissolved oxygen. The cold water acts almost like a biological accelerant.
Exactly. The secondary hypothesis, however, focuses entirely on cellular metabolism. Extreme cold severely depresses the metabolic rate of these organisms. Because their cellular machinery is operating at a fraction of the speed of a temperate organism, their cellular degradation is vastly slowed.
They age slower.
They burn energy at an incredibly low rate, which drastically extends their lifespan. For indeterminate growers, meaning organisms that do not possess a genetic stop switch for growth upon reaching adulthood, a significantly longer lifespan simply equates to decades of continuous physical expansion.
They just keep growing till they die.
Yes.
But the sources indicated a deep frustration within the marine biology community because neither of these mechanisms paints the full picture.
The inconsistency is the true mystery here. I mean, if hyperoxygenation or depressed metabolism were universal laws of the deep Southern Ocean, we would expect to see gigantism uniformly across the benthic community.
But we don't.
We don't. We observe species of colossal sea spiders sharing the exact same thermal and chemical environment with other species of invertebrates that remain microscopically small.
Which makes no sense.
It forces researchers to question whether we are fundamentally misunderstanding the evolutionary drivers of polar gigantism, or if there's a complex intersection of localized pressures we simply haven't mapped yet.
It is wild to consider that we can land sophisticated telemetry rovers on Mars and analyze the chemical composition of alien rocks in high definition, yet we lack a unified biological theory for why a spider the size of a dinner plate exists in our own ocean.
The science is still very much baffled by it.
But the biology of the Drake Passage isn't just about the organisms themselves, it is about the macro-level planetary work they're performing. We have to examine the carbon vault.
This is the precise point where the extreme isolation of the Drake Passage intersects with the daily life of you, the listener.
The air you are breathing right now is chemically altered by the mechanics of this specific body of water.
The data regarding carbon sequestration is almost difficult to conceptualize. The Southern Ocean, driven largely by the churning of the Antarctic Circumpolar Current through the Drake Passage, extracts roughly 600 million metric tons of carbon dioxide from the Earth's atmosphere annually.
600 million tons. That equates to about 1/6 of the total carbon emissions generated by human activity globally. 1/6. How exactly does a chaotic, violently churning stretch of water function as an atmospheric scrubber on that scale?
The mechanism is a massive biological pump, heavily reliant on the upwelling we detailed earlier. When the fierce deep-water currents strike the bathymetric ridges and force nutrients to the surface, the resulting colossal blooms of phytoplankton engage in photosynthesis.
They're plants, basically.
As they multiply, they consume vast quantities of dissolved carbon dioxide from the surface water, converting it into organic carbon within their cellular structure.
And because the surface water is constantly being depleted of CO2 by the plankton, the ocean draws more CO2 directly out of the atmosphere to maintain chemical equilibrium.
Exactly. And once that carbon is locked inside the biological matter, the sheer violence of the passage takes over.
The turbulence doesn't just drive upwelling, right? It creates downwelling too.
Incredibly powerful downwelling currents. As the plankton die, or as the krill that consume them excrete waste, this carbon-rich particulate matter, which we call marine snow, is caught in the chaotic downward currents.
It just gets dragged down.
Violently swept down the water column, descending past the twilight zone, and deposited onto the abyssal plain at depths exceeding 3,000 meters.
And at that depth, surrounded by freezing temperatures and immense hydrostatic pressure, the carbon is effectively sealed in a vault. It remains sequestered in the deep ocean sediment for centuries, completely removed from the atmospheric greenhouse cycle.
The Drake Passage acts as a highly efficient planetary carbon pump. However, leading oceanographers explicitly note that our understanding of the granular physics governing this pump is alarmingly incomplete.
We don't have all the details.
We understand the macro-level input and output, sure, but the microscale fluid dynamics that dictate exactly how the turbulence subducts the carbon and at what rate remain a critical area of active research.
Which introduces a terrifying variable into climate modeling. If we do not possess a complete mechanical understanding of the primary system responsible for sequestering a sixth of our atmospheric carbon, what happens when the thermal parameters of that system change?
That's the million-dollar question.
Right. If rising global temperatures alter the density and flow of the deep currents in the Drake Passage, does the carbon pump stall? Or worse, does a change in upwelling dynamics breach the vault and release centuries of sequestered carbon back into the surface waters?
That potential feedback loop is one of the most critical unanswered questions in contemporary climate science. The Drake Passage cannot be viewed merely as a geographical location. It is a load-bearing pillar of the planet's atmospheric infrastructure.
And as we descend even deeper into the passage, past the descending marine snow, past the carbon-trapping sediment, we encounter organisms that are so fundamentally alien, they force us to reconsider the definition of an individual. We need to talk about the ctenophores.
The comb jellies. They represent a complete departure from the standard biological architectures we are familiar with.
Visually, they look like deep-sea ghosts. They are these entirely transparent, gelatinous forms that pulse with rows of iridescent, light-refracting cilia. The fossil record indicates they have remained largely unchanged for nearly 700 million years.
Ancient.
But it isn't their age that makes them the most anomalous creatures in the abyss. It is the architecture of their nervous system.
To grasp the magnitude of the ctenophore anomaly, we must first establish the baseline for every other neural network on Earth.
Okay, lay it out for us.
Whether you are examining the brain of a human, the nerve cord of a dog, or the neural ring of a standard jellyfish, the fundamental building block is the neuron. And critically, neurons are discrete individual cells.
They're separate units.
Right. When a signal travels through your nervous system, a neuron fires an electrical impulse down its axon, but it does not physically touch the next neuron. There is a microscopic gap called a synapse.
So the electrical signal has to be converted into chemical neurotransmitters to bridge that synaptic gap, trigger the next cell, and continue the chain reaction. The gap is the defining feature of neural architecture.
For almost everything. But the comb jelly doesn't have gaps.
It doesn't have gaps.
It does not. High-resolution electron microscopy conducted by researchers at the Marine Biological Laboratory revealed that ctenophore neural nets are organized as a syncytium.
A syncytium, meaning what?
The plasma membranes of their individual neurons physically fuse together. There are no synaptic clefts. The cells merge to form a single, continuous, unbroken web of neural tissue.
Biologists looking at this data have remarked that the deeper they probe, the more fundamentally bizarre it becomes. Because a continuous fused neural net completely upends our understanding of evolutionary biology.
The implication is staggering. It strongly suggests that ctenophores do not share a common neural ancestor with the rest of the animal kingdom.
Wait, really?
Yes. It implies that hundreds of millions of years ago, the evolutionary tree of life ran a completely parallel, independent experiment in how to construct a nervous system. The biochemical mechanics of how complex information sensory input, motor control propagates through a continuous, fused network without the regulatory checkpoints of synaptic gaps fundamentally challenges our baseline assumptions of neuroscience.
And if a parallel evolutionary nervous system wasn't mind-bending enough, we have to look at the splicing experiment, the creation of the two-moused monster.
This is the experiment that pushes marine biology firmly into the realm of science fiction.
Researchers took two entirely separate ctenophores, two genetically distinct individuals floating in a tank, and essentially pressed their bodies together to observe the biological response. They didn't just adhere to one another like sticky gelatin, they underwent complete biological fusion.
Complete fusion. Within a matter of hours, the cellular structures of the two distinct organisms began to aggressively reorganize and merge. The boundaries delineating the two individuals dissolved, and they functionally became a single organism.
That is wild.
The researchers documented that the two separate digestive tracts physically connected. Food introduced into the mouth of the first jelly would seamlessly travel through the newly integrated gut and be expelled through the apical pore of the second jelly.
But the integration of the nervous systems is the detail that is almost impossible to process. The researchers noted that once fused, the new organism displayed perfectly synchronized muscle contractions.
Instantly.
Right? If they introduced a localized physical stimulus, like a poke to one side of the fused entity, the entire organism reacted with a unified, coordinated response.
And the only mechanical way to achieve that level of instantaneous synchronized motor control is if the continuous, unbroken neural nets of both individuals physically spliced together, creating a unified, shared nervous system.
This plunges us directly into a philosophical crisis regarding the concept of the self. I mean, we strictly define individuality by biological boundaries, where my physical tissue and my localized neural network end and the external world begins.
It's the definition of an individual.
But if two genetically distinct individuals can seamlessly physically merge their neural nets and operate under a unified, shared sensory and motor consciousness, then individuality in the deep ocean is not a fixed law. It is just an illusion. You aren't permanently you. You are simply raw neural material capable of plugging into a broader biological network.
The Utenophore demonstrates that the biological borders we consider fundamental are merely one of many possible configurations. The extreme pressures of this environment clearly force life to explore radical, boundary-dissolving adaptations.
The Drake Passage acts as an evolutionary crucible, warping and shaping the life trapped within it. But when we pull the lens back and examine the grand geological timeline, we see that this 600-mile stretch of ocean didn't just adapt the life within its borders.
It created the world as we know it today.
Millions of years ago, the violent birth of this passage literally constructed the modern world.
Geologically speaking, the Drake Passage is a relatively recent feature of our planet. And its formation was the specific tectonic trigger that plunged the Earth into an icehouse climate.
Let's establish the baseline here. What did the southern hemisphere look like before the Drake Passage existed?
If we look at the paleoclimatological record during the Eocene epoch, roughly 30 to 41 million years ago, the tectonic arrangement was vastly different. South America and Antarctica were connected by a continuous land bridge.
No water between them.
Because there was no oceanic gap separating the continents, the warm equatorial currents were able to travel significantly further south, running directly along the coastlines of the Antarctic continent.
And because the continent was constantly bathed in these warm thermal currents, Antarctica was not a sterile, glaciated wasteland.
Not at all.
The fossil record from this period is incredible. We find evidence of dense, temperate rainforests, complex terrestrial ecosystems, and flying penguins. Well, towering warm water penguins.
It was a thriving greenhouse environment. But the tectonic plates governing South America and Antarctica were slowly diverging. Over millions of years of excruciatingly slow continental drift, the land bridge thinned, fractured, and eventually separated.
And when that happened?
The moment that gap widened sufficiently, the physics of the ocean immediately rushed in to fill the void, giving birth to the Antarctic Circumpolar Current.
That unrelenting 15 million cubic meter per second flow of water we discussed at the very beginning.
Exactly. The formation of the ACC permanently altered the thermodynamics of the planet. It created a massive high-velocity loop of freezing water that completely encircled the Antarctic continent.
Like a moat.
This current functioned as an impenetrable kinetic thermal wall. It physically deflected the global warm currents, completely isolating Antarctica from the equatorial heat distribution system.
It sealed the continent inside a thermodynamic vault.
Deprived of the warm oceanic currents, the temperature of the Antarctic landmass plummeted. Seasonal snowfall stopped melting, eventually compressing into glacial ice. Over millions of years, that uninterrupted accumulation generated the colossal continental ice sheets that currently dominate the southern pole.
Ice sheets that currently lock away roughly 70% of the entire planet's freshwater supply.
50%, yes.
It is the ultimate demonstration of geographical consequence. A single 600-mile rift opens up in the Earth's crust, and the resulting shift in fluid dynamics triggers a localized ice age that aggressively reshapes the entire global climate system.
The paleoclimatology of the Drake Passage forces a very sobering realization regarding the stability of the Earth's climate machinery. We tend to perceive our global climate as a vast, heavily buffered system.
There's something hard to break.
But the geological record unequivocally demonstrates that planetary ecosystems are highly sensitive to narrow specific thresholds. A single tectonic doorway opening between two landmasses was sufficient to transform a lush, forested continent into a permanent frozen desert.
Synthesizing everything we've explored today, we began by looking at the Drake Passage as a purely terrifying maritime obstacle, a sheer test of survival for steel hulls.
But its true nature is so much more profound. It is a planetary crucible.
The exact same towering rogue waves that shatter ocean liners are the mechanisms forcing ancient nutrients into the sunlight to sustain the largest creatures to ever exist. The freezing thermal shock that strips the hemoglobin out of an ice fish's blood is the exact condition required for that fish to survive.
The 600-mile gap of water that sailors refer to as a graveyard is the exact tectonic doorway that froze Antarctica and sculpted the modern, balanced climate we rely on today.
And despite our satellite arrays, our laser telemetry, and our advanced algorithmic forecasting, the Drake Passage remains entirely sovereign.
Untamable. It stands as a constant, violent reminder that human engineering has hard limits. We do not tame this passage. We simply build stronger ships, monitor the atmospheric pressure, and hope the physics of the ocean allow us to cross safely.
It brings us right back to the beginning. A mythological beast that refuses to be tamed. But looking at all of this data, a final thought emerges that ties the biological fragility we discussed directly to the geological history. And frankly, it is deeply unsettling.
It is. We established that the tectonic opening of the Drake Passage permitted the circumpolar current to form, which walled off Antarctica, induced a deep freeze, and generated the colossal ice sheets.
Right.
But this introduces a massive variable into our current trajectory. If atmospheric temperatures continue to rise, as we already see threatening the survival of hyperspecialized organisms like the ice fish, and those massive Antarctic ice sheets begin to rapidly degrade,
they will discharge that 70% of the world's fresh water directly into the Southern Ocean.
how will an instantaneous massive influx of fresh, less dense water alter the salinity, density, and flow rate of the circumpolar current?
Wow.
Could the exact tectonic passage that initially froze the southern pole and stabilized our climate be the very mechanism that, once diluted, unravels the global climate system all over again?
It is a question that the planet is currently answering in real time. Thank you for joining us on this deep dive. Keep questioning the mechanics of the world around you, keep exploring those hidden depths, and we will catch you on the next one.